All right, this is officially my last lecture of the school year, and this is on electrochemistry. So electrochemistry is the study of chemical energy, or taking chemical energy and converting it to electrical energy. You can do this via redox reactions, because if you remember correctly, a redox reaction has electrons transferring from one element to another. So if you can get those electrons to transfer through a wire, then you are creating an electrical current, and that electrical current can be used to power things. For example, if you take zinc and you place it into a solution of copper, what you're going to find is the zinc is just going to give its electrons to copper and make copper turn into solid copper, and then of course the zinc will turn into copper ions. If we assign oxidation numbers to all of the elements in this reaction, you will see that through the course of this chemical reaction, the copper gets reduced and the zinc gets oxidized. So the zinc is quite literally giving its electrons to the copper ions in that solution and producing solid copper and zinc ions. And that process happens spontaneously. It's a spontaneous process, meaning that nothing is driving it as far as like I'm not making it happen. The zinc just gives its electrons to the copper ions. And you can think of the reason why that is because copper is more electronegative than the zinc. The copper ions want those electrons more than the zinc wants those electrons. So if we could separate these two processes, the oxidation process and the reduction process, into two separate containers and run a wire between the two, like this, then when the zinc gives up its electrons, those electrons can travel through that wire, so in this direction, into the copper solution, and that will just happen spontaneously. And of course, if we put something in the middle of this wire, like a load of some kind, like right here, we could put a load. That could be like your cell phone or an iPod or anything that works off electrical energy. Then what you've just done is created a battery. All right, so that electrochemical cell that you just made is called a battery, and there are actually two types of electrochemical cells. So the first type of electrochemical cells is called a galvanic, or sometimes you'll hear them referred to as voltaic cells. These are spontaneous, meaning one atom just gives its electrons to the other atom. Another word for these are batteries. And then the second type of electrochemical cell is called an electrolytic cell. And electrolytic cells are non-spontaneous. And what I mean by that is when you hook them up, so if we were to make the two chambers and hook them with a wire, you would get flow in one direction, but an electrolytic cell is where you force the electrons to go in the opposite direction. So if you think of an electrolytic cell being like a rechargeable battery, so a battery, works where one atom gives its electrons to the other spontaneously and produces some electrical energy. And then if you force it in the opposite direction, what you're doing is you've made an electrolytic cell. So let's talk about what's actually happening in a spontaneous galvanic or a voltaic cell. So what I have here is a picture of what's going on inside of a battery, essentially. All right, so these things right here are called electrodes. So that's an electrode and this is an electrode. And one of them, of course, is made of zinc, and the other one is made of solid copper. Now, for this reaction, right, you can make electrodes out of just about any metal. In this particular reaction, we're talking copper and zinc. They could be any metal, though. And the zinc electrode is submerged in a solution of zinc, so some sort of zinc salt, like say zinc nitrate. So what you really have in this solution is a whole bunch of zinc ions kind of floating around in there, and a whole bunch of nitrate ions floating around in there. Okay, and on the other side, you have the same thing. You have copper, so solid copper, and it's submerged into some sort of copper salt, like copper nitrate. It could be any copper salt that's soluble. In this case, it's copper nitrate. So you've got a bunch of coppers and a bunch of nitrates floating around in there, like this. Okay. All right, this thing right here is a wire, and then this is going to be your load. And your load, again, can be anything that runs off of a battery. So it could be like an iPad or a cell phone or a flashlight or a calculator or a watch or anything that runs off of a battery. So the way that this battery would work is our zinc electrode is made of a whole bunch of zinc atoms. And those zinc atoms are, well, we decided in the overall equation from before that zinc was being oxidized. So those zinc atoms are going to lose 2 electrons each to become zinc ions. And so once that happens, that zinc ion gets dumped into the solution. So all of these, whenever they lose 2 electrons, are going to become zinc ions and you know, end up in the solution. And then those electrons that they lose are going to be pulled through the wire towards the copper because the copper wants them. So our electrons are going to start to leave the zinc and flow through the wire and power our load, and then flow out of our load through the wire into our copper. So notice what happens on our zinc side is we had an oxidation. This electrode where oxidation occurs, we're going to call that electrode the anode. Okay, so at the anode, our atoms in our anode lose electrons, they become oxidized and become an ion. Those ions just break off and float around into the solution, and our zinc, or in this case our anode, is going to shrink because we're losing solid zinc from it. So that anode's actually going to wear down. The electrons from it flow through the wire, through the load, into the copper, where they build up on the surface of this copper electrode. So you're going to find that your copper atom or copper ions are going to be attracted to those negative electrons, and that when they bump up against that, your copper ions are going to gain those electrons to become solid copper. So these copper ions in solution that are floating over here and bumping up against this electrode and picking up these extra electrons are going to go through, of course, reduction. And the copper, when it turns into a solid, is just going to start to stick and build up on the side of that electrode. So you're going to find that this electrode, which, by the way, where reduction happens, that electrode is called a cathode. The cathode's going to start to build up and actually get a little bit bigger. So again, at the anode, your solid anode ion, or atoms become ions by losing electrons. That's what oxidation is. Because they're losing atoms that are becoming ions and going into solution, the anode is going to wear down. Electrons are going to leave the anode, flow through the wire, through the load, power the load, out of the load into the cathode where reduction will take place. The thing getting reduced is actually the copper in the solution bumps up against the cathode, picks up electrons, and undergoes reduction. Becomes solid copper, which is going to start to build up on the sides of this cathode, and so the cathode is going to start to get bigger. Now, of course, this is a spontaneous process. The whole reason that the electrons are doing what they're doing, leaving the zinc and flowing towards the copper, is because copper wants the electrons more than the zinc does. Okay, so what's this thing right here? This thing serves an actual, real, very important function. This thing is called the salt bridge. And without it, none of this takes place. And here's why. So in the salt bridge, you've got some sort of a salt. It could be sodium and chloride, or it could be potassium chloride. Whatever the salt is, it just has to not have the same ions that are in this solution as far as the zinc or the copper are concerned. So what's happening at the salt bridge is you've got to actually go back and look at this solution. So remember, when your zinc atoms are undergoing oxidation to become zinc ions, the electrons are leaving and going through the wire. And these zinc ions that are getting produced are being dumped into the solution. So suddenly you've got this buildup of positive charges going on over here. So what's going to happen is if you don't have something to cancel out those positive charges, these electrons aren't going to want to leave. They're going to want to go into the solution. Instead of going through the wire to the copper, they're going to want to go into the solution because they're attracted to those positive ions. So that's where your salt bridge comes in. You need something to balance out the positive charges, and that's what the negative chloride will do. So the salt bridge serves this function. It dumps a bunch of chloride ions, or rather the chloride ions will move into this solution to start to kind of cancel out all the positive charges that are building up. And then over here, on the other side, you're losing positive copper ions because they're becoming solid copper. So you need something to replace those positive charges so that you don't get this nitrate built up that's negative. So that's where your sodium comes in. Your sodium will come down here, and you're going to get a bunch of sodium ions that are going to help sort of replace these positive copper ions that are disappearing. So your salt bridge actually serves a very, very important function. And without it, the electrochemical cell won't work. All right, so just really quickly, a really good way to remember the difference between your electrodes. So you've got anode is where oxidation takes place, and cathode is where reduction takes place. There's a fun little mnemonic that you can use to remember this, and it is an ox and red cat. So to remember that the anode is where oxidation takes place, that you just remember anox, and that where reduction takes place is at the cathode, remember red cat. So anox and red cat will help you remember which electrode is the anode and which electrode is the cathode. You should also know that the anode is the negative end of a battery, and the cathode is the positive end. So if you ever look at a battery, so let's get a picture of a battery here. On batteries, you'll notice there's a negative end and a positive end. Like it's actually marked negative and positive. And so hopefully you can remember that negative is your anode, and that's where oxidation takes place. So remember anox. And the positive end is your cathode, and that's where reduction takes place. So remember red cat. And electrons will always flow out of the anode and then through a wire and then to your load, whatever it is you're powering, and back to the cathode. So electrons will always flow in this direction, and it makes sense because oxidation is loss of electrons, so electrons are lost on this end, and reduction is gain of electrons, so they're gained on this end. All right, so going back up to this fun battery that I drew. How do we know that this is the direction of electron flow? I mean, like, how do we know that if I hook all this up, so I get this all set up, and I put a wire, how do I know that the electrons are going to leave the zinc and go to the copper? There must be a way to know that. Why don't they go the other direction, I guess is what I'm saying. Like, what makes it so that they always leave the zinc and go towards the copper? Well, the way you're going to know that is you need a table of standard reduction potentials. So a reduction potential is exactly what it sounds like. It is a number or a value that will give you an indication of how likely an element or an ion is to be reduced. Like, how likely is that going to happen? Or how likely is it? So if you look at your table of reduction potentials, the one I'm going to give you in class is actually flipped around. So the fluorine's on the bottom and the lithium is on the top. But you will notice that you are given all the reactions anyway are, they're all reduction reactions. So they're showing the element or ion gaining electrons and turning into something. And then there's a number. That number is expressed in volts. So this EO in volts is called this is a reduction potential. So and that means how likely is it is that gonna happen? So what you're looking for is this. The more positive the number, the more likely that reduction is to occur. So if we look for copper and zinc, now the trick becomes some atoms can form more than one ion. So you can look over here and you can see there's a bunch of coppers actually. There's copper plus 1, there's copper plus 2, and then copper plus 2 plus 1 electron. It's very confusing. The one I'm giving you in class doesn't have this reaction on there, but it does have the other two. So you want to find the correct one. So here's the copper gaining 2 electrons, like we said would happen in that battery. And then you want to find the zinc one, and the zinc one is down here. And what you're doing is you're comparing this reduction potential. So the E reduction, or the reduction potential for copper, is a positive 0.34, and the reduction potential for zinc is a negative 0.76. So because this is a more positive value than this, when I put these two things together, I know that copper is going to get reduced. So copper will get reduced before zinc will get reduced. So that means that in my electrochemical cell between copper and zinc, that I know that electrons are going to flow to the copper, and copper is going to get reduced before zinc. So copper gets reduced, and there's its reduction reaction, which I just copied right there. And the zinc is then going to be oxidized because it's not going to get reduced. So when the zinc gets oxidized, the equation is just this equation right here, but I just reversed it. I flipped it. And our reduction potential for copper is positive 0.34 volts. And that means we need an oxidation potential for zinc. And the oxidation potential for zinc is positive 0.76 volts. So where did I get this number? Well, I got it from here, and since I reversed the reaction, I just reversed the sign. So from these two numbers, I can actually calculate the voltage of the cell. So this is going to tell me my voltage output of my electrochemical cell, of my battery that I made between zinc and copper. So to get that, I'm going to take the potential of the thing getting reduced, and I'm going to add it to the potential of the thing getting oxidized. So remember, the thing getting reduced, we decided was going to be our copper. So I'm going to take its 0.34 volts right here, and I'm going to add that to the positive 0.76 voltage that we get from the zinc, and when I add those two together, I get a positive 1.10 volts. So if I go back to my battery over here, that means that I should be producing 1.10 volts of electrical energy or voltage for my load. That means that that's how much electricity is coming out of that. So coming back over here, a couple of things that you need to know about calculating cell potential. So remember, EO cell, or E naught cell, equals cell potential, or voltage. Things to remember, if it's a positive potential, total, so when you add the reduction to the oxidation potentials and you get a positive output, that means that this is spontaneous, and it's actually outputting voltage, which is good, because isn't that what you want a battery to do? You want it to give off voltage so that it powers your stuff. If your potential is a negative potential, then that means that this reaction is actually taking in energy from your device instead of giving it energy. And it means it's not spontaneous, which means that it needs to actually have energy input into it to make it happen. We're not going to talk about, I'm not going to explain negative voltage to you, other than what I just said. You will have to calculate voltage for reactions, and if that voltage is a negative voltage, then you can just say that that's probably not a good battery and it's not spontaneous. But that's pretty much all we're going to do with negative potentials. All right, so here's an example of what I might ask you to do with this information. So let's say we're going to build a battery, and the battery is going to have iron and potassium in it. And I want to know the voltage output of this. So we're assuming it's a galvanic cell, right? It's spontaneous. Electrons will move from one of these things to the other. So either from the iron to the potassium or the potassium to the iron. And ultimately, when all is said and done, I want to know what the cell voltage is. I'd like to know what the cell potential is. So in order to calculate cell potential, I need to know the potential for the thing to get reduced, and I need to add that to the potential for whatever is getting oxidized, and hopefully, and we want it to be a positive output, so we want it to actually generate voltage as opposed to taking in voltage. So in order to do this, we're going to need that table of cell potentials. All right, so on that table of cell potentials, I'm going to find these things. So let's find the iron first. Now I want to point out, again, there's more than one iron equation. So there's iron plus 3 plus an electron yields iron 2. That's not what we want. We want to make sure that the ion and the metal match up. So we're looking for this one right here. Iron plus 2 electrons yields solid iron. So we've got iron plus 2 and iron. And then we're also looking for the potassium one, and so here's the potassium one right there. So if you look at your EO reductions for iron and potassium, you will see that the iron has a higher potential, a more positive reduction potential than potassium does. So what that tells me is that my iron is going to be the one that gets reduced, So I know that what gets reduced is going to be my iron. It's going to go from iron plus 2 electrons to a solid iron. And that potential is negative 0.44 volts. And my other substance, my potassium, is going to get oxidized. So we need to write the oxidation reaction for what happens to potassium. So potassium is going to go from being solid potassium to potassium ion and 1 electron. And the oxidation potential, of course, is just the reverse of its reduction potential, so positive 2.92 volts. And in order to get our cell potential down here, right here, we are just going to take our reduction potential and add it to our oxidation potential. So we're going to take our negative 0.44 volts, and we're going to add it to our positive 2.92 volts. Make sure you get a positive number, because if you don't, you did it wrong. And that should give you a cell voltage of positive 2.48 volts. So if I were to actually make an electrochemical cell with an iron electrode in an iron solution and a potassium electrode in a potassium solution, and I hook it up, electrons should flow from the potassium to the iron, right? Potassium is getting oxidized, so it's losing electrons. And the reduction, of course, is a gain of electrons. Remember, oil rig. So these two reactions should take place, and the voltage of my cell should be about 2.48 volts. And just really quickly, I just want to go back and mention, because we drew this big electrochemical cell right here, and we talked about how this just happens spontaneously, and that this would be a galvanic or a spontaneous cell. Remember we talked about how your copper electrode is going to gain mass, and it's going to get bigger because these copper ions are becoming copper, and the zinc is going to lose mass because it's turning into zinc ions. People always ask, well, what happens then? Well, eventually, you're going to run out of this zinc, and then your reaction will stop taking place because you're out of the thing that's getting oxidized. But if it were a rechargeable battery, then what you could do is run voltage through it, 1.10 volts as a matter of fact, to force the electrons in the opposite direction. So you're actually forcing the zinc to take electrons and build up this zinc ion or anode again. And then the copper, of course, would go back to being copper ions. And then you've basically recharged your battery. So that's how a rechargeable battery works. It runs out of energy because you've run out of your anode. So you plug it into the wall, and it forces electrical energy in the opposite direction to build your anode back up so that you can use your battery again.